So hello everyone, this is Ari from pantech. Okay, is my voice clear? Is the screen is visible? Guys, so we will get into the session today. Okay, anyone in the chat box? Okay, so we will wait for 1 minute to guys to join the class. Okay, so before that, in previous class we saw the UART communication and we have developed the UART communication code. Okay, so today we are going to see is I2C communication, which is inter-integrated circuits. Okay, so we will get into the topic. So first we have to know what is I2C. Okay, so the I2C will have two wires. So one is serial data, one is SDA, which is for serial data, and one is serial clock, which is SCL. So not like USART, it will also communicate in only two wires. Okay, then it is a serial communication. So in previous session I have said what is the difference between serial and parallel communication. When it comes to serial communication, it is going to send the bits by one. So that is what serial communication is. Okay. So next, its maximum speed is up to 5 Mbps per second. Okay. And when you come with I2C, we can connect unlimited masters and unlimited slaves. When you come with SPI, we can't connect unlimited masters. Only we can connect the multiple slaves. So we can have only one master in the SPI communication. So when you compare with the UART, we can't communicate more than 2 UARTs. So only they have final the I2C communication. So we can connect unlimited masters and unlimited slaves. Okay. So for example, if you take a car means it will have lots of microcontroller in it, and we will have lots of sensors also. The sensors will come under the slaves, and the masters are the microcontrollers which is placed in the cars. So that is what this communication is. Next, so I2C is a combination of SPI and UART communication. Okay. So this is a communication which is developed later after the SPI communication and UART communication. So they have reduced what are the problems in those two communications. They have rectified those problems in this communication. So it is a synchronous communication. So what is the synchronous and asynchronous communication? What is the difference between both? So synchronous means it will use the clock pulses for transferring the data. When it comes with asynchronous mode means that it will transfer the data without the clock pulse. Okay, that is what synchronous and asynchronous communication. Okay. Now we will see how the I2C works. Okay. So first is addressing. So I2C does not have a save select pin. So when you compare with SPI, you will have a save select pin which is dedicatedly given. So when you come with I2C, it is not based on the save select pin. So it is going to send the address to the slave. So if those addresses match means then it start to transfer the data or request the data from the particular slave. So that is what I2C starts working. Okay, then we have a read and write bit. So the single bit at the end of the data frame. So low voltage will be to write and the high voltage to read. Okay. So next is data frame. So we will have an acknowledgement bit after every data frame. So data frame is as a long of 8 bits long, and each data frame has an acknowledgement bit. Okay. So after transferring the data, the acknowledgement will be set as logic 1 to give that the information that the data has been transferred. Okay. So the data are, when it comes to I2C, the data are sent in the message format. Okay. So it is going to send the data in the message format. So each message contains the binary address of the slave. So we will see detailedly how it is working. Okay. So this is how the I2C transmission is. So first thing what is going to do is the master is going to send the start condition to the every slave. So consider we have connected the 3 slaves. Okay. By how it is sending the start condition? By switching the SDA line. Okay. So this is how it will send the start condition. Then the master will send the address to the slave. So after the address is sent, these are the address for the slaves. If these addresses matches means, then the master will start to send the data to the specified slave which address is matched. Okay. So you can see in this picture the slave 3 has an address match. So address is matched in this slave 3. Then the data will be transferred to the slave 3. Okay. So next, slave will compare the address and the acknowledgement bit is pulling the SDA loud. So by this, we can know that the microcontroller will know that we have selected the address has been matched. Okay. So next process what it is going to do is, next the master will send or receive the data frame. So the master, this is how the serial data will be given to the slaves. It is in the bit form. So you can see it, right? So 0, 0, 1. It is how the data are transferred to the slaves. So the master will send and receive the data from the frame. After data transfer, after transferring the data, it receives the device, returns the acknowledgement bit. So the acknowledgement bit is having in all the data frames. So after transferring the data, the acknowledgement bit will be written as a logic on. So by that we can know that the data has been transferred. Okay. So then to stop the data, the transmission master sends the stop condition. So we have to send the stop condition to stop the data transmission by switching the clock line I. Okay. So this is how the SPA is transferring, working. Okay. So you can see we have in SPA we can connect the multiple masters and multiple slaves. So this is single master and multiple slave connection. This is a multiple master and multiple slave connection. So this master can communicate with these all the slaves and send and request the data from these slaves. So when you come with multiple slaves and multiple masters, so any of the master can send the data to any of the slave, and any of the data can be requested from any of the slave by any of the master as per the coding. Okay. So this is how the communication is working. Okay. So next we will get into. So guys, you can now convert this masterclass into internship. So you will have a 1 month internship on embedded systems. So this internship is going to provide you valuable skills, and it is going to give lots of in-depth knowledge and details in the about the STM controller and embedded systems. So we have lots of courses in pipeline. So like CAN protocols, RIN protocols, all going to be get added in this internship, guys. So use this coupon code to get a discount of 509. So the fees is 1200. By using this coupon, yes, ESMC1, you can get the internship fees as 691. So guys, the batch is going to get, and the batch is going to start from now in coming Monday. So guys, use this internship, and you will what are the benefits you are going to get using this internship. So we will see that. Okay. So you will have a 30 days of live session, and you can have a 90 days of access for the records. Okay. And the hands-on practice on the embedded projects. So we are going to develop lots of projects in an internship, and you can have a one-to-one mentor live session with me while you are developing those projects, which is teaching by me. If you have any doubts, means you can interact with me directly in every Saturday class, which is a master live one-to-one session. So guys, you can ask questions directly to me. Okay. So and we will provide you after registration. We will provide you an internship confirmation letter and the internship certificate. So internship certificate it is going to be 2 internship certificates. One is for participation and one is for close completion. Okay, guys. So use this benefits and get upskill in your embedded system domain. Okay. So the registration fees is 1200. The coupon is ESMC1 and discount is 509. So what is the final fees is? It is 691. So guys, use this link to. So the link will be provided in the chat box, guys. So don't wait for the time. So click this link and register now and get use of it. Okay. So this is the internship, which is going to give you lots of knowledge to you. Okay. So next we will get into the RCC registers. Okay. Before getting into RCC registers, we have to know what are the steps we have to do. Okay. So we will see that first. First, we have to give create a function for system I2C configuration. So inside the configuration, what are the things we have to do? We have to configure the system clock, and you have to configure the GPIO as an alternative function, and you have to initialize the I2C, and you have to start the I2C condition. So you have to give, then you have to, after starting the condition, what my master have to do? It have to send the address and check whether the address is matching with the slave or not. If the address matches, then the data will be sent or requested from the slave, which is the address matcher. Okay. So then it will send the address, and you can write the data to the address, and you have to then give the stop condition. Then you have to give if you want to print an hello world in a string means, if you want to give a string means, you will create a string function also. Okay. So next step is, so this is the in-depth explanation. So first we will initialize the I2C. So we will enable the I2C clock, then we will enable the GPIO's clock, then we will select the alternate function, we will select the mode of GPIO as an alternate function, and we have to set the ABB frequency in the I2C register, and we have to give the CRR value, and we have to set the T raise value. So these are all the things which I will show you coming slides. Okay, then we have to finally enable the I2C. Okay, so in this installation you can see that we are going to set the CRR value and T raise value and ABB frequency. So we need to derive the CRR value and T raise value, right? So how will you derive it? Okay, now you will see it. So this is a formula for deriving the CRR value. Okay, so it is by clock divided by I clock divided by P clock. What is we going to use? Okay, so now we will see it. So how we are going to select this value? Okay, now we have to go to the reference manual. Okay, wait a second. Go to the reference manual and you can see open and go to the electrical characteristics and you can see the communication. Okay, wait. So you can see the communication interfaces and we have an I2C characteristics. So you can see here we can find all the microcontroller will have a default values for the clock. So we have to, what are the values we need? So we will see that. So we need we need to know TR value and TW value, and we have to know the T clock, TP clock value. Okay, so we will search for those values in this datasheet. So you can see the TW value is we have a low clock time and high clock time. So we are going to use this high clock time. Okay, so when you come with high clock time, it is in the microseconds. Okay, we have to convert it to the nanoseconds. Then it is 4.0 into 1000. So what this value will be? It is equal to 4000. Okay, then we need is TR of SCL. What is the value? Maximum value is 1000. Okay, now we have to know the TP clock, right? So we will go to the formula. So by referring the datasheet, we have set the value for TR and TW. Okay, then what is the T clock values? So the T clock value will be derived as equal to, see, you can see it. So T clock is equal to 1 by what is the P clocks megahertz. So what is the P clock frequency we are using here? So we are using is 16 megahertz of P clock frequency. So I have to divide it by 1. Okay, I have to divide 1 divided by 16 megahertz. So we have to give plus 1 value to it. So what is the value will be? So 1 divided by 16 megahertz will be 0.0625. So we have to convert it into a nanoseconds. So if we multiply it with the nanosecond means it will be 62.5. Okay, so that is why the reason is we have given this T clock as an 62.5. So finally we get a CRR of value of 80. If you do this calculation means you can get the value of 80. Okay, so now we have find the CRR value. Okay, so now we have to know the TR value and we have to derive the T raise value. So we have a T raise value is equal to, we have a formula for it, default formula is equal to TR of SCL divided by TP clock of 1. So what is the TP clock of 1? It is 62.5. And what is the TR? It is 1000. Okay, so then we have to add plus 1. So what is this is? The microcontroller will add 1 to it. Okay, this is the formula for it. So we have to add it 1. So this is the T raise means it is a maximum frequency to which the frequency can go. Okay, so we have to go, it is, if you divide this value means you will get a 16. Then if you plus 1 it means it will be 70. So we have derived the CRR value and T raise value. Okay, so next we will get into the start condition. Okay, so start condition I2C and we are going to find a start condition and I2C address. Okay, so what is the start condition? So the start condition is I2C. We have to start the I2C condition, start condition in the control register 1. Then we have to check whether the condition is started or not. Okay, so then is I2C address. So send address to the data register. So wait for the address to get set. So we have an address flag. When the address is matched, the ADDR register will get set and gives a flag when the address is matched. Okay, then we have to clear the ADDR. So we have to read the SR1 and SR2, which is a status register. Okay, so next is write function. So then you have to send the data to the data register and wait till the TXE bit is set. So as you can see it in the UART communication, we will wait for the TXE to set. So we will wait for the DXE2 state that indicates the data register is empty. So if the data is transferred, then the register will be get empty. So we have to wait till this register is get set. Then we have to give the stop condition. So the stop condition is, you can see it in the CR register 1. Okay. So guys, we have seen what are the steps to do it. Okay. Now we will get into the registers. Okay. Go to the reference manual. And what is the first thing we have to do? We have to enable the clock for the I2C. So go to the block diagram. So what is the I2C? We are going to use this I2C 1. Okay. So you can see the block diagram. Wait. So I2C 1 is, so I2C, wait a second, I will I2C. You can see the I2C 1 is connected to the ABB bus 1. Okay. So its maximum frequency is 142 megahertz. But what is the frequency we are going to use? We are going to use this 16 megahertz of frequency as a peak clock. Okay. So we have to configure we have to see the APB1 register. So go to the reference value and go to the APB1 register. So this is a reset and clock enable register. So you can see we have an I2C in this 21th bit. Okay. So first we have to set logic 1 in this 21th bit. So as this 21th bit. So you can see the I2C 1 clock enable. So first thing you have to do is enable the clock. Okay. So we will get into the I2C registers. Okay. So the first is the control register. Okay. What did we have in control register? Okay, we will see it. So we have a peripheral enable bit. This will enable I2C. Then we have in control register 1 we have a start generation. In master mode it will repeatedly start the generation. When it comes to save mode, it starts the generation when the bus is free. Okay. So next is stop generation. So when it comes to stop generation, so it is going to be, we have to set logic 1 to in this 9th bit to stop the generation of the I2C. Okay. So next we will see is software reset. Okay. So this is don't need of it, because if you want means you can reset this peripheral, and you have to send logic 0 to this bit. If you didn't send the logic 0 to this bit, means the I2C will be in under the reset state. Okay. It will not work. So next is control register 2. So we will not use this DMA request, all these things in this specified video. All these things we will comment in the upcoming sessions. So we will see what are the requirements we need. Okay. So we will see the first is in the control register 2, we have to set the frequency. Okay. So we have to select the peripheral clock frequency. We have to give what is the frequency it is running. Okay. So we will give the frequency in this 0 to 5th bit in the control register, second control register. Okay. So CR of 2. Okay. So wait. So what is the frequency we have to give here? So we have to give us what is the peak clock we are using. What is the ABB bus frequency? It is 16 megahertz. So it is running in the 16 megahertz of frequency. So we have to give the 16. We have to left shift the 16 by to the 0th position. Then we will attain the value what is we needed. Okay. So next we will come to the data register. So the dedicated bit is from 0 to 7 and rest of the bits are reserved. So we will send the data and receive the data in this same register only. Okay, as like the UART. Okay. Then we have a status register 1. Okay. So in status register we have a data register empty bit. We are going to check. We will wait till this bit is getting set up, and we will have a data register not empty bit as like same as a UART communication. So we saw it in the last class. Okay. So next we will see the, so you can see ADDR is here. So this will say the address is matched. So this bit is get settled when the address matches the master and slave. Okay. So you can see the start condition generation. So we have to set logic on this bit. Okay. So we will check whether this bit is we are in status register, so we will check whether the condition is started or not by using this only. Okay, so this bit only. Okay, so next is status register 2. Okay, so we will not going to use this status register 2. Okay, so we will come to the next section. So CRR. So we have we have a dedicated bit for CRR is from 0 to 11. So we have already find the what is the value we are going to give, and we have seen the formula. Okay, so what is the value we have to going to give? So what is the value we have derived by using the formula? We have derived the CRR as an 80. Okay, so we have derived the CRR as an 80 and the T raise as an 17. Okay, so we have to give the value in the registers only. Okay, so we will get into the registers back. So we have to give the 80, we have to left shift this 80 to this 0th bit. So the value will be considered in this all the bits. Okay, so we have seen this CRR value setting. Then we have a T raise register. So the maximum rise time in SM and FM. So master mode. So these bits should be provided the maximum duration of the clock feedback loop in the master mode. So this is the value we are going to give, which will provide a maximum duration of the clock pulse. Okay. So we have to set 17 to this. We have to left shift this 17 to the 0th bit. Okay. So next we will not use this filter sort. So we have seen the registers. Okay. Then we will get into the code. Okay. So you will get into the KEIL. Okay. KEIL ID. So as we already configured the system clock in this last class, so we will just make a copy of it. Okay. Then we will create a new project. So first we have to select the what is the controller we are using. Okay, STM of 2F407 VG. So this is the controller which we are using. Okay. So we have to give the SIMSYS code. Then we have to give the startup file, add the startup file in the device. Then we got. So first thing we have to create is we have to add the .c file. So we will type this .c. I2C of. Okay. So we have now added the dot file. Okay. So now we have to we have to first do, we have to include the startup file. Okay. So first hash include of. So which series we are using is 407. Okay. So what are the functions we are going to create? So we are going to create this void of system clock void. Then we have to init the I2C. So we will create the init I2C of void. Okay. So next function is we have now initialize the I2C. Then we have to start the I2C. So void of start condition. Okay. So void. So next thing we have to do is we have to write the function. So we have to write the data to the I2C, right? So for that, write of int of data. Okay. So we will make the variable as a data. Then what is the function we have to do? Then we have to send the address and the stop condition. Okay. So void of, we will make it as an address add. Okay. Address of void. So we have to send the address, right? So we need to give an sign of add. Okay. So this is a function which is going to send the address to the slave. Okay, then what we have to do? We have to stop the I2C condition. Okay, so void of stop. So this will stop the I2C. Okay, void of. So now we have created the stop function. Then we have to, if you want to send the string, then what you have to do? You will do void of. You will give it as a print. Okay, so print of unsigned. Okay, so int of. We are going to declare here a pointer. Okay, so star of dead. So this pointer is going to add the address, and as per the address, it is going to display the data. Okay, so next we have to give us what is size. We have to say the size of the data we are sending. Okay, so again unsigned of int of size. Okay, so these are the functions we are going to create. Before that, we will also create the delay function. Okay, so delay of, wait a second. So delay of ms. So int of delay. Okay, so we are going to create this all the functions. So as we already see the system clock configuration in the previous class, so we will just make a copy of it. Okay, so it will take a time while we are developing. So we will see the directly enter into a I2C concept. Okay, so we will copy the system clock configuration from the UART communication protocol, which we have already developed yesterday. Okay, so this is the system clock configuration. So now we have set the system clock configuration. So what is the next thing we have to do? Next thing is void of init I2C. Okay, well, C. So void. So we will wait a second. You will get into the slide. So this is the initialization. Okay, so we will select all. Okay, so we will make it done. So first thing, we have to enable the clock for the I2C. So where we have to enable it? We have to go to the registers, go to the RCC registers, in that APB1 EN1. Okay, it is AHB. So APB1, you can see we have an I2C one in this 21st bit. Okay, so first we have to enable this. We have to send logic to this 21st bit. Okay, so we'll send RCC of on left shift off. You have to send logic to the logic 1 to the 21st bit. Okay, so this will enable the I2C clock. Then we have to enable the clock for GPIOs. So which is the register we have to see? We have to see is AHB1. Okay, so in AHB1, what is the port we have to configure? Before that, we have to see what is the, we have to get into the pin diagram. Okay, before that, get into the pin diagram. So wait a second. So what is the port having SPI1? Wait a second. So you have to see the, we have an I2C one of DA in the PB of 9, and we have a SCL in the PB of 8. So we are going to use this the pin 8 and 9. So we have to enable the clock for port GPIO B. So we will get into, again we will go to the registers. So what is the register we have to, what is the port we have to give the clock pulse? So we have to configure the first bit as a clock. So we have to give the clock, enable the GPIO port clock. So we have to send logic 1 to this, then first bit. Okay, so now we will send the, So RCC of, in which bus it is having, it is in the ABB AHB 1 of EL0. So one left shift of 1. So this is going to be enable the clock for GPIO port B. Then we have to select this alternate function. So we will get into the, again we will get into the pin diagram. Sorry, we go to the data sheet. Okay, go to the GPIO registers. In that, go to the alternate functions. So when it comes with the from 0 to 7 pins means we will configure in the low register. When it comes with the last 7 pins means we have to configure in the high register. So what is the pin we are configuring? We are configuring this pin 8 and 9. So we have to select the high register for giving the alternate function. So what is the alternate function number? What is this represents? What is the AF we have to do? So we will get into the, we will see the GPIO function description. Okay, so function description, see the alternate function. So we will see that we are going to connect this, use the pin is 8 and 9. So we have to see I2C one is AF4. So alternate function, if you give the alternate function as AF4 means it is going to configure those pins as an I2C one. Okay. So we will now we will get into the register. I register is here. Okay. So what is the value we have to give is AF of 4. So 4 means we can simply send the logic 1 to the, we are using is 8 and 9. So you can simply send the logic 1 to the second bit, second position. You can simply left shift the 1 to the second position and the sixth position, or you can send the value as an 4. So what I am going to do is I am going to send the 4 to 4. I am going to left shift the 4 by to the 0th position. So it is going to automatically set the logic 1 in this second position, and I will also going to send the 4 to this 4th bit. So it automatically going to set the logic 1 in this 6th bit. Okay. So we will configure it. Okay. So GPIO of, which is the port B. So B of, what is the function which we are using is, what is the register we are using? We are using is I register, right? So we will send the left shift the 4 to the 0th bit, and we will left shift the 4 to the 4th bit to set the alternate function. Okay, as an AF4 of 4. So this is going to set the pin PB of 8 and PB of 9 as an I2C communication pins. So next is we have to set this motor register. So we have to set the register as a motor register. We have to say that we are going to use the alternate function. So go to the registers. Motor. So what is the pin we are using is, we are going to use this 8 and 9th pin. So we have an 8 and 9 here. So for alternate function we have to give logic 1 to the 19th and 17th bit, or you can simply send the 2 to the 16th and 18th bit. Okay. So now we will send the motor register. Okay. So the GPIO A of B motor. So this is going to send the, we are going to simply left shift the 2 to the, which is a bit I have to left shift it to the 16th and 18th bit. Okay. So I'm going to simply left shift the 2 by 16 and 2 left shift of 18. Okay. So this is going to set the alternate function in those pins. Okay. So next thing, what is the thing we have to do? So next thing is we have to set the ABB frequency, CR value, T raise value, and finally we have to enable the I2C. Okay. So first we will go to the registers. So go to the I2C registers. Okay. So first thing we have to see the control register 2. To give the frequency we are using. What is the frequency? We have it in the P clock. So what is the frequency we are using as a peripheral clock frequency? It is 16 MHz. So I have to send the 16 to this 0th bit. So first we will send it. Okay. So in which register? In I2C of 1. In I2C CR of 2. Control register 2. So we are going to send 16 left shift of 0. So it is going to say the frequency what is we are using, what is the peripheral clock frequencies. Next is CRR register. Okay. So we will go to the directly go to the CRR register. So we have a CRR register. So we have to left shift the 80 value which is we have derived from the formula. So our CRR value is 80. So we have to left shift the 80 to this 0th bit. So the value will be get settled evenly. Okay. So I2C of 1 CRR. Okay. So we are going to 80 left shift of what is the pin, what is the register 0. So this is going to send my 80 to the 0th bit and the frequency is set. Then what is the thing we have to give? We have to give us T rise. Okay. So where is the T rise? So we will come with the T rise register. So we have to send what is the T rise value? It is 17. Okay. So we have to send 17 to this 0th bit. So I2C of 1 of T rise. Okay. So this is going to send 17 to the 0th bit. So now we have set the T raise value, CR value and ABB1 frequency. Okay. So next thing we have to, what is the next thing we have to do? You have to enable the I2C register. Okay. So we have to enable it, the I2C register. In the, where is this bit is present? It is present in the CR1 register. Okay. So go to the CR1. In CR1 you can see the 0th bit as an peripheral enable. So you have to send logic to the 0th bit. So to enable this peripheral, okay. So we will send I2C of in CR1 register. So CR1 of 1 left shift of CL. So this is going to enable my I2C. Okay, now we have created the initialization function for I2C. Next, what is the thing we have to do? We have to write the function for start condition. Okay, so we will. Okay. So start condition. So the start condition bit is in CR of 1, control register of 1. So we will go to the register now. So in control register, you can see we have a start generation bit as an 8th bit. So if you send logic 1 means the repeatedly going to start the generation. Okay. Oh. Then we will check whether the generation is started or not in the SR register 1. So where is this SR register 1? SR means it is a status register. Okay. So in status register, you can see we have a 0th bit as a start condition flag. So this bit is going to set when the condition is started. Okay. So we are going to check it with this bit only. So now we will write a code. Okay. So I2C of 1 is equal to which is a register we have to use it. It is in the CR control register 1. Okay. So we will shift it by, so in the 8th bit. So we have it in the 8th bit, which is a start generation. Okay. So we will have the R2. So then we have to check whether the condition is started, right? So go to the I2C 1 of SR of 1. I'm going to check it with the 0th bit. So 1 left shift of 0. So this is going to check whether the my I2C condition is started or not. Okay. So equal to 0. So this bit is get settled when the condition is started. So now we have write in the code for start condition. Next, what is the thing we have to do? We have to send the address, right? We have to send the address to the data register. Okay. So we will create the address function first. Okay. So first we have to send this address to the data register. So we have a data register in I2C as like a UART I2C of 1 is equal to data register. So we are going to send the address here. So what is the value we are giving? The 880.100 with 0 cross of F. So now we have centered the address. We have to check whether the address flag is set or not. So what is the address flag is going to do is, wait, go to the status register. So we have an address flag. So if the address is matched, this flag is going to get centered. So we have to check to this. So create a while function. So in while function, you have to go to the status register of 1. So I2C of 1 register. So I'm going to check it with the first bit. Okay. So 1 left shift of 1. So it is going to check whether the address is matched or not. Okay. So equal to 0. Then finally, what is the step we have to do? So finally, we have to clear the address bit. So for that, how we will create? By reading the status register 1 and 2. So we will create a dummy variable. Okay. So unsigned off. Temporary variable. So we are going to read the status register 1 and 2. Okay. So I2C of equal to SR1 I2C 1 SR of. So now we have read the status is 1 and 2. So this will clear the address bit. Okay. So now then what is the, if the address is matched up, then we have to send the data. Okay. So now we will write the function for writing the data to the slave. Okay. So now we have to send data to the data register. Okay. So I2C of 1 is equal to dr is equal to data. So this will send my data to the data register. Then I have to wait till the data register is getting empty. So what is the bit we have to check? We have to check is the TX data register empty bit. If this bit is centered, then the data has been transferred. So it is in the 7th bit. Okay. So we will give the while, we will create a while condition, while of I2C of in the status register 1. Okay. So SR of 1. We done it with 1 left shift of. What's the bit we are using? In the 7th bit. The TXNE bit is in the 7th bit. So we will equal to 0. So it will wait till this condition is getting satisfied. Okay. Now we have written the data to it. Then we have to write the stop condition. So we have to stop the I2C condition, right? So we will develop the code for I2C stop condition. So stop condition. So simply we are going to stop the I2C generation. Okay. So it is in the CR1 register. So we are okay. I2C of CR1. So you can see we have a stop generation bit in the 9th bit. So we have to send the logic 1 to the 9th bit. Okay. In the I2C of CR1. So I 1 left shift of 9. So it is going to stop my I2C condition. Okay. So next, now we will create a function for printing. We have to send the string in the I2C communication. Okay. So we are going to so what is the thing we have to do? We have to declare the string pointer of data and the size. Okay. So first thing is we have to check whether the TXE is set or not. Okay. So while of so TXE is in the status register of 1. Okay. So I2C of SR1 going to under with 1 left shift of TXE is in the 7th bit, right? So 7th bit, I am going to check it with the 7th bit. So equal to 0. So it is going to wait till this bit is get a set. Okay. After setting, then we will create a while. So while of size. So it is going to run till this size. So create the, then what is the thing we have to do? Then again we have to check whether the status is set or not in the 7th bit. So TX bit is set or not. Okay. So again we have to check this condition. Okay. So next is we have to send the data to the data register, right? So we are, as we use the pointer function, so we are going to add the data by adding the address. So it is going to add the data in by index form. So it is going to start from 0 to index 2 till the what is the size. Okay. So we will go to the I2C of data register. So what is the thing we have to do? We have to create the volatile unsigned of int, because we are going to send the string, right? So signed off. Okay. Then I'm going to add the address with the data. Okay. So I'm going to add the string with my data. Okay. So data of plus plus. So it is going to add the data with the adding the address by from the index of 0. From the index of 0. So it is going to send the one by one from the value we are having in the index 0, then it will send the index 1 value, then it will send the index 2 value by adding the address. So the pointer is going to give the value and both was address. So that is what pointer is. Okay. So next is we have to decrement the size. Okay. So we have decremented the size. Okay. Then we have to check whether the busy state bit is empty or not. Okay, set it or not. So we go to this register. So you can see that register in the SR1. Okay, so go to the SR1 register. SR1 register. You can see it in the second bit. Okay. So you can see the bit transfer is finished. So if this bit is set, means the data transformation has been completed. So we have to wait till this bit is get settled. So it is in the SR1 of second bit. So we will create a while for it. Okay. So while of I2C of 1 is equal to SR of 1. It is in the SR1 register. Okay. So we are going to check it with the second bit. So we have it in the second. So we have to wait till this bit is get settled. Okay. Then now we have created the print string function. Okay. Then we have to create the, what is the next thing we have to create? We have to create this delay. So we are going to create a software delay. Okay. So we are not going with timer. So we are going to create a software delay. Okay. So what is the this delay is going to do is, first you have to give the init of I. So give this init of I, go to the for of that's a delay. Okay. So delay 0. Okay. So delay of minus, and again you have to create the for of I is equal to 0 of I is greater than of 9. So 3195. So this software delay is going to give you a perfect millisecond delay. Okay, without using the timer itself, we can create a 100 millisecond delay, 1000 millisecond delay by using this. If you give the 1000 delay in milliseconds, means it's going to be act in the exact 1000 milliseconds. Okay, so this is a software delay for creating in a milliseconds. So I of plus plus. Okay, so now we have created the delay. So we will compile this code now. Okay. So guys, we have an error here. So what is the error? We didn't give an int main function. So we have to create the int main function. Okay. So main. Okay. Main of void. Okay. So okay. So what is the thing we have to do? First we have to initialize the system clock, right? So we will initialize the system clock. system block. So which is we have already defined the function in the upper. Okay. So next is we have to init the I2C. So we have an init I2C function. So next is we have to create a while of 1. So in that what we have to do? We have to start the condition, then we have to send the address, then we have to write and stop the condition, and we are going to give a delay for 25 milliseconds. Okay. So we will write it. Okay. So start condition. So start the condition. Then we have to send the address, right? So add of. So what is the function we have defined? It is in the address of. What is the address? So we are going to give a 0 cross of 4e. Okay. So what is the 4e means? I will explain it in the next class. Okay guys. So today we will develop the code. In next class we will interface the slave with the STM32 controller. Okay. So this is the address for the I2C slave. So I will show that slave in the coming classes. Okay. So we will just develop a code here. Okay. Okay. So next is I2C of write. Okay. So we have to write the data, right? So write off. What is the thing we have to do? I'm going to write the value. Okay. 0 cross off. So 0. So it is going to tune on the LED, first LED in my I2C IC. Okay. Then what we have to do? We have to stop the condition, right? Stop off. Then we will add a delay. Okay. Mass of 35. Okay. So finally we have. So we have created the wait. So then we will compile this. Okay. So we have no errors. Okay. So guys, in next class we are going to interface with the I2C module. Then we are going to send the data from the STM32 controller to the I2C module, and by configuring the I2C as in a slave mode and the STM as in a master mode. Okay. Okay guys.